Hi guys, in this section we'll be talking about another transformation called a reflection, which I kind of have the reflection title reflecting, which is pretty cool. But anyways, we're going to be doing all of these examples as a class together, so you don't really need to watch this on your own unless you are absent, or maybe if you're ahead you want to go ahead and watch. But again, we're going to do it in class anyway, so you might as well just wait till we do it in class. Alright, so let's get going. So again, a transformation is the change in position, size, or shape of a geometric figure. Okay, which we talked about translations, and today we'll be talking about reflections. Okay, which a reflection is also another type of isometry, which is, remember, is a transformation that does not change the size or shape of a figure, which this is called a rigid motion. So this has the shape reflecting over the x-axis, and then from here it reflects over the y-axis, and then from here it reflects over the x-axis. So if you see the shape, although it's flipping over, it does not change shape or size. So it's also a rigid motion. Cool beans, right? All right, let's keep going. So in class, we brainstormed where we saw reflections in our world, which is pretty cool. Some that I came up with, which you can see a reflection in water. It kind of mirrors the image. You can see a reflection in glass, like I got this giraffe and the cat looking in the window. Cool. You can also see it also in a mirror, like if it's mirroring itself, then a mirror. But also, like with dancing, if you dance with a partner, you guys can kind of mirror each other or kind of look the same on both sides. So that could be another example of a reflection. So a reflection is a mirror image of a specified line. So there's supposed to be a line drawn in called the line of symmetry or axis of symmetry or line of reflection. And if you imagine like this was a piece of paper and here was our line of symmetry, if I were to fold along that line, both sides would pretty much match up. So that would be my line of symmetry. Or if you flip some over the line, they should look the same after it flips. So reflections have symmetry. And they'll be symmetric to the line that you're actually going to reflect over. So like here's a pre-image, then bam, it has flipped over the y-axis. So my y-axis would be the line of symmetry, or the axis of symmetry, or the line of reflection. And again, here's the pre-image also reflecting over the x-axis. So in this case, the x-axis would be your line of symmetry, or axis of symmetry, or line of reflection. All those mean the same thing. Okay. So in class, you were given these 3 points. You were supposed to plot them on this lovely graph. Then using your patty paper, you were going to reflect your shape over the line of reflection to get your new point. So when you did the activity, F, when we flipped it over the x-axis, went to -1, -3. G, when you flip it over the x-axis, went to -5, -1. And H, when you flip that bad boy over the x-axis, it became -2, -5. So if you were not here when we did this, you should be filling this out on a nifty piece of paper. So I have a paper that looks just like this. So if you don't have the paper, make sure you get it from me. And then so looking at these points, I asked the students in class to see if they noticed a pattern for how we could get from the pre-image points to the image points without having to like flip over a piece of patty paper to figure out where it would land. So let's see here. Like F was -1, 3, but then it became -1, -3. G was -5, +1, but then it became -5, -1. Okay, this H was -2, +5, but after reflected, it became -2, -5. So do we see any of the point values changing between the x or the y? Or what do you think we could do to these points to get to these points? How did the coordinates change from the pre-image to the image? Holy hot dog, you guys are like geniuses. Okay, if you guys notice, the x's stayed the same, okay, but the y's, they changed sign. Whoa, holy hot dog, right? I know. Okay, so the rule we're going to follow, on your paper there's a little spot where you write the rule. Okay, this is what the rule looks like. So we're going to start with our pre-image point, and then the pre-image will become, that arrow shows what the pre-image will become when it gets to the image. So if you see here, the x stays the same, but the y is negative. Like, see, all my y's were negative, but you have to be careful. That negative does not mean your points are always negative. What that means is actually the points will change signs or become the opposite value. So if they're all positive, then they would become negative. If they're all negative, then they would become positive. So be careful. That sign means negative. So again, keep the x-coordinate the same and change the sign of only the y-coordinate. Be careful. So I left the middle for you to practice the rule if you wanted to. So for practicing the rule x negative y, okay, what I did, since x doesn't change, I went ahead and filled in my x's. And then my y's will all have a negative in front. So I'm just going to put my y's right in front of that spot, and bam, they all transform into a negative. And those would now be my points. Okay, so if this had been a -3, then the negative sign would have been in front of the -3, and the double negative would have turned it positive. So that's why it's not necessarily negative, it's changing signs. So be careful. Okay, then we did a funzie, which was awesome. Sorry you missed out on it. Anyway, so example 2 was the same idea, except now we're reflecting over the y-axis, so get excited. So again, we have our 3 points. We have E, which is at 6,3, and then we flipped it over the y-axis and got -6,3. We have D, and then we flipped that thing over the y-axis, and it became -5,2. And then we have F, or sorry, not F, geez, Miss Long. We have C, and then we flipped that thing over the y-axis, and it became -2,4. So again, in class, we used patty paper to actually flip the points over to get the new points. But you don't have to do that. So do you guys see a shortcut to get from our pre-image points to our image points? What stays the same? What has changed? Oh man, you guys are so smart. If you guys see here, the y stayed the same, but the x changed signs. Oh man, that's pretty cool. Okay, so our rule this time would be -xy, which means you keep the y-coordinate the same and change the sign of the x-coordinate. So again, that negative does not mean it's always negative. It means it changes the sign of the x-coordinate. So if you wanted to practice your rule in the middle, all I did was I filled in my y's because they're not changing. Then I put negative signs in front of my x's and then just bam, filled my x's in. And those are my points. So that's how you can use the rule. Pretty cool, right? Let's keep going. That was another funzie you missed out on. Sorry, guys. But anyways, example 3. Now we're reflecting over the line y equals x. So this orange line right here is our line of reflection, which that is the line where every single x value will equal every single y value. So all your points, x and y, are the same on this line. Like we have 0, 0, 1, 1, 2, 2, 3, 3, -1, -1, -2, -2. So that's kind of how you can get points to draw on that line. So again, in class, we graphed these and then used our patty paper to reflect over. So we got -5, 9 and flipped that thing over and got 9, -5. We had -2, 3, flipped that thing over the y equals x line and we got -3, 2. We had -1, 5, we flipped that thing over and then we got 5, -1. So again, do you notice a pattern? Is there something going on with the pre-image points and the image points? Let's see. They kind of look the same. Numbers are the same, but they don't look like they're in the same spot. So, You guys always know the answer. You guys are so smart, I don't even know why I teach you. Okay, so that is correct. So if you guys see, the x's all become the y's, and the y's become the x's. So guess what, you guys? X and y switch spots. So the rule for reflecting over the line y equals x is to have x and y trade places. So do not change any signs. That's when the demon cats will get you, so watch yourself. So if you want to practice the rule, again, I just put my x's in the y spot, so bam, they're in the y. And I took my y's and threw those things up in the x spot. And that would be how you get your image point. So that is the shortcut. Let's keep going. Another funzie you missed. Try not to miss class so you don't miss out on these funsies. Okay, so lastly, we were reflecting over the line y equals negative x. Okay, so again, this is the line where y is the opposite of x. Remember, that negative sign means opposite, not necessarily negative, so be careful. So again, to get your points for the line of the reflection, whatever x is, y is the opposite. So like at -1, y was 1. At -2, y was 2. At +1, y was -1. At +3, y was -3. So that's kind of how you get the points for that line of reflection. So again, we plotted these. We used our patty paper. We flipped things over this line. So we started with L. We flipped that thing over the line, and we got 4, 7. Then we went on to K. We flipped that thing over the line and got -4, 1. Then we went on to J, and we flipped it over the line, y equals -x, and got -3, 2. So again, oh, you didn't see that. How did the coordinates change from the pre-image to the image? I'm seeing they're kind of looking the same, but they might be in different spots, and something about the signs are different. Holy hot dog, you guys are right, like normal. Okay, so the rule for reflecting over the line y equals x is you not only flip x and y, so x and y trade spots, but also you change both of the signs. Like it was -7, -4, they flipped and changed signs, so it went to 4, 7. It was -1, 4, but they flipped and changed signs. So pretty cool, right? So if you want to practice the rule, all I did was I filled in my negative signs, and then I just flipped the x. I put x in the y spot, so bam. And I put y in the x spot, so bam. Okay, now, again, you don't have to do it this way, so I filled in the negatives, because we have a negative y and x. Okay, but remember, all those negatives mean are opposite. So you don't have to do it this way. As long as you know it's the opposite, you can just change the sign right away. Okay, but here, so I put a negative in front of my -4, which a double negative will be positive. And I put a negative, the negative here, in front of my x, which was -7, and then it transforms into a +7. Same thing here. I had a -1. I put my negative sign in front of it, and bam, it'll turn positive. So again, you don't have to do it exactly this way, but that's kind of what's going on in the background. That's like what secretly is happening. Okay, so again, they flip and change signs. That is the rule for y equals -x. Okay, and again, we did another funzie. Sorry, you missed out on the fun times again. Sorry. So here are all the rules together just to kind of sum up what we learned about reflecting over lines and their shortcuts. You don't necessarily have to use these rules all the time. Like, for example, when you're reflecting over the x and y axis, which I didn't really talk about this, I forgot to, but technically, since we're reflecting it over, sorry guys, over the x-axis, like G, since this is the line of symmetry, they should be symmetric or mirror each other over that line. So since G is 1 space above the x-axis, when it flips over, it will be 1 below. Since F is 3 spaces, I think, hold on, let's see, 1, 2, 3, yeah, 3 spaces above the x-axis, when it flips over, it goes 1, 2, 3 spaces below. Okay, so you could also count when you're reflecting over horizontal and vertical lines. Now, y equals x, you can't really count. It's a little bit more complicated. And again, if you're reflecting over y, we could have counted. Like C is two spaces to the y-axis, so when it reflects over, it must be 2 spaces on the other side. D was 4 spaces, I think. No, 5, JKLL. 5 spaces to the y-axis, so when it flipped over, it flipped over 5 spaces. So you could also count. You don't have to use the shortcut, but some people like the shortcut. So this kind of sums up what the shortcuts are. Okay, so then after this, then we were reflecting over very specific lines. So not any special line like these, and these won't have rules. Okay, so on this one, we are reflecting J, K, and L over the line y equals 2, which y, when it's y equals a number, that's a horizontal line. This tells you it will intersect y at 2. So it's a horizontal line that hits the x-axis at 2. Okay, if it's an x equals, then it's a vertical line that hits the x-axis at whatever it says. Okay, so we have our line y equals 2. And we want to reflect the points J, K, and L over this line. So, again, in class, we did this. You could trace this on your patty paper and flip it over the line to figure out where it will be. But probably, in my opinion, is just to count, like I just explained. So, like, K is 2 spaces over my line of reflection, which means when it flips over, it'll be 2 spaces under. Okay, L is, let's see here, 1, 2, 3, 4, 5, 6 spaces above, so it'll go 6 spaces under. And J is 1, 2, 3, 4, 5 spaces above, so it will go 5 under, like so. Sorry guys, I had a class coming in, so I thought it would not be a good time to finish recording my video. So, again, on this example, example 5, I plotted points J, K, and L, and we're going to reflect it over the line y equals 2, which is a horizontal line through the point 2 on the y-axis. So again, if you count the spaces, it's really easy to reflect over. So all I did was I started with J, I counted how many spaces it was above, which was 1, 2, 3, 4, 5, and I flipped it over, counted 5 spaces under. Went to K, counted 2 above, so when it flipped over, it went 2 below that line. And then L was 1, 2, 3, 4, 5, 6 above, so when it reflected, it went 6, 1, 2, 3, 4, 5, 6 below. So that's all I did to get my points for the image. Fun times. Let's keep going. So the next one, again, same graph, if you guys see, same J, K, and L. And then I'm reflecting it over the line x equals -1, which when it's x equals the numbers, that is a vertical line, okay, that hits the x-axis at -1. So it kind of tells you what point it hits on that axis. So if you see here, the line smacks the x-axis at a -1. So that's a vertical line at -1. And again, all you have to do to get the points for reflection is to count to that line. So like L is 1, 2, 3, 4, 5, 6 spaces to the line, so I would count 6 spaces on the other side to get that point. J is 2 spaces to the line, so it's going to be 2 spaces on the other side of the line. And K is 1, 2, 3, 4 spaces to the line. Let me double check. 1, 2, 3, 4. Yep, to the line, so it's going to be 4 spaces on the opposite side, which will give you this nifty image triangle and those points. All right. That's it. So let's keep going. On 7 and 8, you're going to be doing the opposite of what we just did. So on example 7 and 8, I have given you the image and the pre-image shape, which I know this one's the pre-image because it doesn't have the primes. This one is the image because it does have the primes. So I've given you the pre-image and the image, and you have to figure out where is the line of the reflection. So where's the line that I can draw my picture such that these two shapes will be symmetric to that line? Or basically you're finding the line that's halfway in between the two shapes. So like looking here, I can see in between C and C prime, there are, let's see here, 1, 2, 3, 4 spaces in between. So the line is going to be in the middle, which means it would have to be 2 spaces above. So 1, 2, and it would have to be a horizontal line in order for this shape to flip upwards like it did. So this is going to end up being the horizontal line at -1, because -1 is 1, 2 spaces above and 1, 2 spaces below C and C prime. You could have also done the same thing counting the spaces in between A and A prime, or B and B prime, or D and D prime. Okay, and since it's a horizontal line, I know it's y equals, and it smacks the y-axis at -1. So that would be my line of reflection. Now looking at example 8, this one would have to be a vertical line to get this shape to end up over here. If it was horizontal, it would have like flipped upside down and landed over here or something. So I know it's a vertical line, and I want a line that's halfway in between my points, which C and C prime are both on the y-axis, so that one's a little tricky. Let me count some other spaces. So I'm going to start with A. A is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 spaces to A prime. So halfway would be 10 spaces. So it's 10 spaces from A is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the y-axis is actually our line of reflection, which that line is the y-axis, but it's a vertical line, and it hits, remember, vertical lines are x equals, horizontal lines are y equals. So the y-axis hits the x-axis at 0. So it is a vertical line, and it smacks the x-axis at 0, and so the equation for the y-axis is actually x equals 0. So that would be my line of reflection for that one. Pretty nifty, right? Okay, now the next slides on the PowerPoint pertain to a reflection activity that we did in class. I'm not really going to go through the activity with you. This is something we're doing in class, but I'm going to give you some background information. So after we talked about reflecting things over specific lines, now we're going to talk about reflection symmetry or line symmetry. Okay, so I want to find lines that will slice things in half or make it so one side of a shape looks identical on the other side if you were to flip it over. Or like if you thought this was a piece of paper and you folded your picture along the line of reflection, it should match up if you were to fold it on top of each other. So like the stop sign has several lines of reflection. It has one here. Here, so the first one was kind of like in between or in the middle of the sides. This one kind of goes through the corners. Oh, see, this one kind of goes through the corners of the octagon. So this shape actually has lots of line of reflections. They go through the middle of each side as well as the corners. So you could have like that, you could have that, etc. Now the honeycomb, we're going to ignore the little bees. We're just going to look at the little hexagon. So this one actually has two lines of reflection. Do you see a line that I could draw on this picture where it would be symmetrical on both sides? Oh my goodness, you guys are so smart. There is one right down the middle. If you were to fold this half on top of that half, it'd be the same. And there's also one horizontally in the middle. Nifty. Now let's take a look at this star down here. Where can I draw lines that would slice this thing in half? Oh man, you guys are so smart. Okay, pretty much if you draw a line from the tip of the star to the other side, on each tip, if you do that, it will slice it in half. Like, bam, here's one, here's one, here's one, and there would be another one. But I'm not going to show that one to you. And then the butterfly actually only has one line of symmetry. Do you spot the line of symmetry? Well, actually, hold on. Before we talk about the butterfly, I wanted to go over one more line with the star. I forgot. So this line is not a line of symmetry because if I were to fold this in half, this would not match to that side, or this half is not identical to that side. So be careful. So the butterfly has one line of symmetry. Do you see it? Do you see it? It would go straight down the center of the butterfly. So if you were to fold along that line, then each half of the butterfly would be the same. But this one, if you follow this way, the top half does not look like the bottom half. So that is not a line of symmetry. So the next objects I'm going to talk about, these are what you're going to write on your paper. There are three little definitions that we're going to go over at the very top of your paper. So symmetry allows a shape to be carried onto itself by a reflection or rotation. So you can have symmetry with reflections and rotations. So get excited. Line symmetry means a shape has symmetry. So if you were to draw a line on that shape, then it will have symmetry or will be symmetrical on both sides. So it is a figure that can be mapped onto itself by a reflection through a line. And the last word that you're going to write on your paper is line of reflection. So the line of reflection, which is also called the line of symmetry or axis of symmetry, is the line through which a figure can be reflected such that it's carried onto itself. So line symmetry means it has lines of reflections And the line of reflection is the actual line that splits a shape in half. So these three you should copy down onto that paper if you are not able to do it during class. So some objects have lines of reflection and some don't. Like look in here, the heart only has one line of reflection. The A only has one line of reflection. These are the only lines that will divide that shape in half and make two exact objects on both sides. Now this one has 4 lines. If you divide it any of these ways, it'll look identical on either sides of that line. Same with the triangle. The triangle has 3 lines of reflection. So some shapes have only 1 line of reflection, while others have more than one, which is pretty cool. Now others is kind of sad. Other shapes don't have any lines of reflection. Like this Z, it kind of looks the same on both sides, but if you were to fold this on top of the other side, it would not match up. Okay, so that doesn't work. This one obviously does not look the same on both sides. Same with this one. This one kind of looks the same on both sides, but like the Z, if you were to fold this along this line on top of itself, this corner would be over here. That would not line up. And same with this little raindrop or teardrop looking thing. I hope it's not a teardrop because that'd be really sad. But yeah, so some objects have lines of reflections and some don't. And then during class, you guys did the activity and you learned more about lines of reflection. I do have this picture posted though, so if you were absent, you can at least get the picture and fill in what you missed. So the last part of the activity in that packet that you're on goes over symmetry in regular polygons. So at the very bottom of one of the pages, there's a definition that you can fill in for regular polygon. So you need to write this at the bottom of that paper. So a polygon, a regular polygon is a polygon that is both equilateral, which means it has all congruent sides, and equiangular. Try saying that 5 times fast. That's a weird word. Equiangular means it has all congruent angles. So it's equilateral, it has congruent sides, and it's equiangular, which means it has congruent angles. So all the sides are the same, and all the angles are the same. That's what it means to be a regular polygon, which is exciting. So some examples of this are an equilateral triangle, a square, a regular pentagon, hexagon, heptagon, and octagon. So these shapes don't have special names when you get above 4 sides. So we just call it a regular pentagon, a regular hexagon, a regular heptagon, a regular octagon. If you went up to 12 sides, it'd be a regular dodecagon. 10 sides, a regular decagon. So again, we don't usually give special names. That's kind of sad to shapes above 4 sides. But 3 sides, when it has equal sides and angles, it's equilateral. And if it has 4 sides, if it has equal sides and angles, it's called a square. Okay, and lastly, at the very end of the activity, you guys found out you were kind of seeing how many lines of symmetry these regular polygons had. Which an equilateral triangle had 3. A square had 4 lines of reflection. A regular pentagon had 5. A regular hexagon had 6, and a regular octagon had 8. So do you notice a pattern between how many sides the figure has and how many lines of reflections it has? Holy hot dog, they are the same. So regular polygons, if you look over here, regular polygons have lines of symmetry equal to the number of sides and angles that it possesses. So if it has 10 sides and it's a regular figure, that means it has 10 lines of symmetry. So that only applies, though, if it's regular. So all the sides and angles have to be congruent. If it's not regular, you can't be assuming that it has the same number of lines of reflection. So be careful. And guess what? That's it. So if you weren't here, that's what you missed. Fun times.